Hello everyone, this is our first video on from chapter 1 dealing with expanded form and base 10 blocks. So I'm going to go through section 1.1 from the book and talk about some of the more important elements from the book. Okay, so chapter 1 starts off with a pretty fundamental idea, and that's the idea of the counting numbers. And so the counting numbers are the numbers that we use, well, to count. So if you think about the numbers that you use to count, I'm going to guess that you don't start counting at 0, you don't start counting at 5, you don't start counting at -20, you start counting at 1. You see 1 of something, and then 2, and then 3, and then 4, and then you might keep going. And so we'll see these 3 dots right here. We'll see these come up during the semester. And that just means that these numbers keep going. There's no largest counting number. You may get to a point and just kind of stop and be done with counting, but there's not a largest number. So we're going to start with this set of what we call the counting numbers. When we count something, we're getting this idea of what we like to call in math the cardinality. So the cardinality of a set is just a fancy word for how many things there are. Ooh, that's terrible. Let's fix that. So the cardinality is how many. So if I were asking how many students are in this class, I could also ask what is the cardinality of students in this class, and then people would look at me like, why are you using that word? But it means the same thing. It just simply means how many of these things that we have. Now, it's important that we make the distinction between number versus numeral. Now, number is the quantity that we have. We can think of this as our cardinality. We count these things through, and then we determine how many we have, and that becomes my number. Now, once I have that number and I assign it some sort of symbolic representation, that becomes the numeral. Now, this is really important because if we have, let's say, objects like this, and a student goes through and counts, and we see that they are going through and looking at each one of those, and then the student may write that. And if you see that they are counting 1, 2, 3, 4, 5, 6, and they might even say 1, 2, 3, 4, 5, 6, they could have the correct quantity knowing that there are 6 objects here. So they know the number, but they've written the incorrect symbol. They've written that the symbol for 7, obviously, as opposed to 6. So if you were to see this just on the surface, it'd be really easy to think, well, the student miscounted, or the student doesn't know their numbers, or the student saw that there were 7 things instead of 6, when in reality, the student just has the wrong connection, has the wrong correspondence between the quantity and the symbol, the numeral, right? So this is a really subtle distinction between number and numeral, and you'll hear a lot of people use these two terms interchangeably. They do not mean the same thing. And the younger of student that you're working with, the more important it is that you understand this distinction between number and numeral. So why base 10? Well, you could probably think of a bunch of reasons why base 10, but the most obvious one is it's the number typically of fingers and toes. And so the first bit of counting that you do, you see students do, is on their fingers. And so this is the commonly accepted answer for this, is that it's what we have on our fingers. What we mean by base 10, however, and this is going to be an important topic for this semester, what we mean by base 10 is this is the size of our groupings. So this is my grouping size. What that means is when I have 10 of something, it moves to the next value, it moves to the next place. So if you were to think about how we sort of group things, we typically group things in tens. And so then we would know how many tens we have, how many ones we have, and then we can extend that even further. Once I have 10 tens, that becomes a 100. Once I have 10 100s, that becomes 1,000, and so on and so on and so on. Before we get into thousands and 10,000s, though, I mean, we can see a pretty direct example of this. I have a number in mind. So if I were to have all of these sort of tick marks, and I want to know how many there were, for the most part, students will, should be able to go through and count all of these things individually, but they'll start to notice that it's a really inefficient way to do it. And so as we go through and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we could take, where was I? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's 10 right here. And I could group this into a group of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can put that into a group of 10 like this. And then I count 1, 2, 3, 4. And so now that makes the counting an awful lot easier. Instead of having to count 24 things individually, really I only have to count 6. I have to count one group of 10, another group of 10, and then 1, 2, 3, 4. And I can count this and see, well, that this is 10, this is 10, this is 4. And so the whole thing together, I count to make 24. So I can see how much this is, and the counting becomes an awful lot easier. Now, this will become this idea of place value. I can write how many tens I have here, and I can write how many ones I have here. And so I know I have 2 groups of 10 and 4 ones. I wouldn't say a group of 1 because that just sounds kind of awkward. But this is what I mean by grouping size. Once I have 10 of these units together, they become a group of 10. These don't have any here. And if I were to have 10 groups of these, if I were to have 10 groups of ones that made a 10, 10 groups of those 10s would make 100, and so on and so on and so on. So there's a connection here between these groupings that we make and this idea down here of place value. The position of my digits, so these individual numbers here are called digits. So the position of my digit tells me something about the size of the grouping. So in this first place will always be ones, the next will be groups of tens, so on and so on and so on. So this base 10 is a crucial piece of that. In some classes, you will look at bases besides 10. You'll look at base 2, you'll look at base 8, you'll look at base 16. And so all that changes is how big these groups are. We're not going to be doing any of that in here, but just be aware that you will see that in some other classes. And you may even teach from a curricula that does that sort of thing. So this is a very fundamental idea that I want to make sure that we address, and this is that our numbers that we use are a combination of 2 things. They use the idea of place value, and they use the idea of digits. So a student might not fully understand the distinction between this number and this number, or even this number. To a lot of students, this is a 1 and a 4. And this 0, you might even hear a student say, well, that 0 doesn't matter because it doesn't have any value. Or a 0 isn't worth anything, so it doesn't do anything. And what that lets you know is that student doesn't understand the distinction between that 1 being here or that 1 being here. That the place value inherent to these 2 numbers is very, very different. Or that this 0 represents something very different than this 0, and what it does to that 4 is very different. So understanding how these two ideas of place value and digits, how they work in concert, is crucial for students being able to understand how to construct accurate numerals that reflect the number that they are working with. It's a very, very, very important. I mean, it's a fundamental idea for students to understand how these two ideas of place value and digits work together. Um, yeah. So if we were to look at these and talk about what these ones mean, we could even take another number. We could put, say, 41 up here, and we could ask students, well, how is this one different from this one, different from this one, or are they the same thing? Or even better yet, open it up as a very open-ended question to say, how are those ones the same and how are they different? And we know that they're the one because they're all the same digit. So that all those ones have a value of 1, but the place value is different between the three. And so that digit here is a 1, is a 10, is a 100. This gets us to this idea of expanded form. And so expanded form is a way of making this place value idea a little bit more explicit. So if I were to have a number like 152, again, we want students to understand that that 1 is not just a 1, and that 5 is not just a 5. That this is really 150 and 2. It is a 100, a 50, and a 2. That 1 is not just a 1, it is a 1 in the hundreds place, so it is 100. That 5 is in the tens place, so it represents 5 tens. And that 2 is in the ones place, so it represents 2 ones. Because of this, sometimes you'll see this expanded form written out even more explicitly like this. And so now we can see the digit and the place value, how they're working together. So this is 1 in the hundreds place. This is 5 in the tens place. This is 2 in the ones place. Now, students have to be really careful with this, and one of the reasons why you won't see this until some of the older grades is because there is order of operations very implicit to this. Students who work this left to right won't get 152. They'll get 1 times 100 is 100, plus 5 is 105, times 10 is 1050, so on, so on, so on. So there is an idea of order of operations here that we'll come to a little bit later that's pretty crucial. So if students don't understand order of operations, or PEMDAS as you may remember it, this may be sort of a target for later. We may want to hold off on that until we know students can understand that. But this should be able to make sense to students as soon as they can understand addition, or at least the combination of sets. This idea of how we use the addition symbol here, we can make that as explicit or implicit as we want. But we want students to understand that this 152 can be deconstructed. We can open it up into this expanded form. Also, we could do the same thing with a number like 15. Oh, it's not equal to anything. What am I doing? Another problem here. So let's say 1502. And so now the students will be able to see the distinction between 1502 and 152, because that 1 is 1000. And so now the distinction between that 1 and this 1 is very clear. That 1 is in the thousands place, it represents 1,000. This 1 is in the hundreds place, it represents 100. Now, one of the ideas that we'll talk a lot about this semester are the ideas of concrete versus abstract. Now, this is not concrete like you're laying a foundation or making a sidewalk or something. This is concrete like where students are able to work with something in a very sensory motor kind of way, to use the sort of Piagetian terms. It's when they're able to like touch something, hold something, move something around, And then abstract is when it starts to become something that's very symbolic. And so typically we want students to make this transition in this direction. We want them to work with something, touch something, hold something, and really get to experience it. So they're going through some experiential learning. And then from doing that, they'll start to notice, like, man, it's a lot of blocks. I don't think I need all these blocks. How can I do this symbolically so that it becomes a little bit easier to do? It becomes a more efficient or effective method of solving a problem. So we need this to start off with because it's how we sort of understand things in our most basic, intuitive, innate way. And we need the abstract because it becomes an easier, more efficient way to do it. You'll see people complaining about this thing on social media all the time where a student is working on a problem and the child or maybe even the parent has misunderstood the assignment and they think that they're supposed to go get 1,000 blocks in order to model some sort of multiplication problem. No, they were using blocks earlier to do the concrete modeling, but by the time they get to a problem that's that large in scope, there is an abstraction. Now, what happens? What we're going to look at a lot this semester is the stuff that's sort of in between. We'll look at these sort of intermediate models where it's still concrete, but we're abstracting a little bit. So maybe we're still using blocks, but we're taking those blocks to mean different things. And that's what we're going to be looking at here in just a moment. So this is not a binary. We're not just going to go concrete, then abstract. We're going to start with the concrete, and then as students are able to make these abstractions, we'll move more and more further into that abstract. So for a lot of cases, there's a lot of steps in between, and different students will be at different steps. Some students will need to be very concrete for a long time. Some students will come in with a certain degree of abstraction already in their minds. This is part of the challenge of it being a teacher, is understanding where students are and getting them in the right position to where they're doing work that's meaningful and challenging to them. So if we go back to the number that we just had, say our 152, we can think about ways to concretely represent what that 152 might be. We could do something like popsicle sticks and then give a student 152 popsicle sticks and say, okay, well, what's going to be an easy way to count these? And like we said, we're going to think about these ideas of groupings. And so we give the students rubber bands. They could take 10 popsicle sticks together. And so they would make, a group of sticks like this, and then a group of sticks like this, and then a group of sticks like this. And then they're going to get 15 of those bundles. And so then so here's 7, 8, 9, 10. So they've got these bundles of sticks. Now they could take a rubber band and put it around those. And so now each individual stick is a 1. It's a unit. Each of these smaller bundles is a 10. And then this larger bundle, so this is a 10. And then this larger bundle is going to be 100. And then if you had enough popsicle sticks, a big enough rubber band, and enough patience, you could do the same thing with 1,000. And so once you start asking students about that, well, if I had 10 of those hundreds and bundled those together, what number would that make? That becomes an abstraction. You're talking about this concrete model. You're talking about the popsicle sticks that they've just used to do this, but now you're asking them to extend that into some sort of thinking where they're not actually using the popsicle sticks, but they are using popsicle sticks from a previous problem to understand that. So we're somewhere between concrete and abstract, but we're making that move into that abstraction. We may not write 1,000, we may not use that symbol, we may not talk about this, times 10 or anything like that. We're not going to the far end of abstraction. We're just doing it as a little bit more of an abstraction. Another common model for this that we'll use are base 10 blocks. And so we'll have this piece here. We'll go ahead and do all of them here. So we've got this one, we've got this one, we've got this one, and then we've got this one. And so this looks like a little exclamation point. That's not what it's meant to be. This one is commonly referred to as a unit. It is the single block, and it represents the value of 1. So that would be my unit. That would be the same, analogous to my single popsicle stick. This piece here is called commonly a long. I didn't come up with these names, but it's called a long, and it represents a 10. So this would be like our first bundle of popsicle sticks. Then in this long here, when you see them, and I'll send you a link where you can kind of get a better idea of these, you'll see that these are made up of 10 units. And usually they look like 10 units that are kind of like been fused together. And so instead of just being a stick that doesn't have any demarcations, you could take 10 of these units and set it aside those long, that one long, and it looks almost identical. Then we've got this piece, which is called a flat. And so it would be made up of 10 longs. And so if you were to take 10 longs and push them together, it would look almost identical to one of these flats. That makes a 100. And then we have this piece up here, which we're not going to use an awful lot, but we'll see it some. But this is called a block. It represents 1,000. And as you might imagine, it looks like a whole bunch of flats kind of stacked up. And if you were to take 10 flats and stack them on top of each other, it would look nearly identical to a block. So we're going to use these base 10 blocks a lot to describe and to model a lot of the problems that we're going to do. So this is going to be sort of our de facto starting concrete model for just about everything we're going to do in this class, especially in the first part of this class. So if you've worked with base 10 blocks before, cool, you got a little bit of head start. If you haven't, like I said, there's a link on Moodle that'll go to a base 10 block website, and so you can kind of play around with it a little bit and get an idea of what base 10 blocks are like. Two more quick ideas, and then we'll be done with this video. The first one is the idea of a whole numbers, or the set of whole numbers, rather. And so at the end of this section, the book sort of mentions this idea of the whole numbers. And you might be thinking to yourself, well, aren't whole numbers and counting numbers the same thing? Almost. The whole numbers are the set 0, 1, 2, 3, 4, and so on, which looks an awful lot like the counting numbers, but you'll see the distinction here is that the whole numbers include a 0 and the counting numbers don't. Now, some of you might also be thinking, isn't -4 a whole number? Isn't -12 a whole number? What about the negatives? Aren't they whole numbers? Yes and no. We're going to come to that a little bit later on. You are correct in that they don't have decimal or fractional parts, and so they are in a way whole numbers, but the way we sort of define whole numbers with students this age is that it's going to be this set 0, 1, 2, 3, 4, 5. Some people will call these the non-negatives. They're the values that are not the negative integers. But we'll come to that idea a little bit later on when we introduce negative numbers. So this doesn't come up an awful lot. You do need to know the difference between the two. You should know which set is which. But most importantly, don't use the two things interchangeably. Don't say whole numbers when you mean counting numbers, and don't say counting numbers when you mean whole numbers. The last thing that we need to talk about quickly is this idea of a number line model for doing the sorts of problems that we've been talking about. And so a number line, I'm going to assume that everyone has seen one of these at some point. So we've got a line, we're going to show a 0 here. One of the things that's really interesting about a number line is if we were to give a student a problem like the 152 that we've been looking at during this video, and ask a student to sort of show where 152 is, they might do something like 100 here and then 152 here. And it would give us a really good opportunity to talk about how if this is 100 and this is 52, how this picture kind of doesn't work. not all students make the connection right away that there should be proportionality of distance in a number line and that 52 can't be as big as 100. We're assuming this is a linear scale, so there's no way that this is going to work. And so either this 152 needs to move a little bit closer, or this 100 needs to move back a little bit. I'm sorry, needs to move forward a little bit. So something needs to move so these things are proportional. And so it's a pretty common mistake to see students make. It's a really easy mistake to make, so we want to make sure that we address that with students when we can. If we were to do this, let's make this 152 out here. So we could do this also using our idea of expanded form. And so this is a really common exercise that you'll see students sort of being asked to do at the elementary grades, is to show where a number is on a number line using this idea of expanded form. And so we know that our 152 is 100 plus 50 plus 2. And so we could show this as this 100. And then we could either do this whole thing as 50, or some students will do this as 10, 20, 30, 40, 50. And so again, that's doing this as 5 times 10 rather than 50. And so they're using that digit and that place value together. And then lastly, we've got the 1, 2. So we've got our 152 out here. So this could be our 2 like that. So this is a linear model for showing it instead of an area model, which is what we're using with the base 10 blocks. Some students will lean more one way or the other. It's important that you know multiple models for representing these things. We have our symbolic model, obviously just writing the actual symbols. We have that concrete model of using toothpicks or popsicle sticks and using bundles of those. We've got this number line, which becomes a lot more of an abstraction because we're using a lot of symbols, but we're using this concrete line to show how those symbols work together. And we've got our base 10 blocks, which are a little bit more concrete than the number line because we've got one block that represents different values. But they're still concrete because they're pieces. I mean, they're things you can actually pick up and work with. So make sure that you understand all these different models, and we'll talk a little bit more as the class goes on about when one might be more appropriate than another. All right, that's section 1.1. I know it was a lot of review, but there's a lot of foundational ideas to this and a lot of definitions. So make sure that you know what all these terms mean and make sure you understand the difference between them, especially ones that are easily mistaken like number and numeral or counting number and whole number. All right, thanks.